Good day to everyone. Our group is going to present how to use linear programming to solve financial application. In this presentation, we are going to interpret a potential problem that will be met by International City Trust in its investment plan. Financial institutions use linear programming to determine the mix of financial products they offer, or to schedule payments transferring funds between institutions. Linear programming can be used to choose the most suitable mix of financing such that the overall cost of capital is kept to a minimum, or specific constraints on types of borrowing are maintained. Linear programming also can be used to choose between a variety of available projects such that risk and return are optimized, while respecting constraints like maximum break-even period or hurdle rate. Mathematically speaking, the goal of linear programming is to optimize the value of the objective function given the constraints placed on the variables that define it. This is an example. International City Trust invests in short-term trade credits, corporate bonds, gold stocks, and construction loans. The board of directors has placed limits on how much can be invested in each area. We can refer to the table as shown on the screen. International City Trust has 5 million to invest and wants to accomplish two things. The first thing is to maximize the return on investment over the next 6 months. And the second thing is to satisfy the diversification requirements set by the board. The board has also decided that at least 55% of the funds must be invested in gold stocks and construction loans, and no less than 15% are invested in trade credit. Variables in the model are x1 equals to dollars invested in trade credit, x2 equals to dollars invested in corporate bonds, x3 equals to dollars invested in gold stocks, while x4 equals to dollars invested in construction loans. After analyzing the instructions from the board of directors, we can convert the linear programming to standard form, as shown at the left-hand side. And we can obtain the objective function for the maximum interest and at least 11 constraints as shown at the right-hand side. After that, we can input the data into QM as shown at the table. In the end, the output from QM will be the results of linear programming. We can conclude that the maximum interest earned is $712,000 by investing $750,000 to trade credit, $950,000 to corporate bonds, $1,500,000 to gold stocks, and $1,800,000 to construction loans.
The optimal solution is represented by the value x1 750,000, x2 950,000, x3 1.5 million, and x4 1.8 million. The value of lower boundary and upper boundary indicates that the range of objective coefficient can change before the optimal solution will change. For x1 from 0.07 up to an upper limit of 0.11 and lower limit of negative 0.62, the optimal solution will not change. For x2, we have 0.15 for upper limit and 0.07 for the lower limit. For x3 and x4, the upper limit will be infinity and the lower limit will be 0.11. What will happen if the unit interest earned on x3 decreases to 0.09? Based on the table, the lower boundary for x3 is 0.11, therefore, the optimal solution will change if the unit interest earned on x3 decreases to 0.09. What will happen to the optimal solution if the unit interest earned on x4, that is the coefficient, increases to 0.2? Based on the table, 0.2 is between 0.11 and infinity. Therefore, the optimal solution will remain optimal, but the total interest earned now becomes 802,000. Next, what will happen if unit interest earned on both x1 and x2 are changed to 0.1? Note that this sensitivity report only accounts for one change at a time. So, if there are simultaneous changes, we need to check the sum of the ratio changes to allowable changes is within 100% by using 100% rule. If the sum of the ratio is over 100%, the optimal solution may no longer be valid. The proposed increase for x1 is 0.1 minus 0.07, which gives 0.03, with an allowable increase of 0.04, giving a ratio of 0.75. Whereas for x2, the proposed decrease in x2 is 0.11 minus 0.1, which equal to 0.01, and the allowable decrease is 0.04, and giving a ratio of 0.25. The sum of this ratio is 100%, which is within 100%. Hence, the optimal solution will remain optimal, and the total interest earned is 725,000.
Next, we will see about the changes in right-hand side value of constraint. Before we start, let me introduce myself again. My name is Moh Wei Xian, matrix number 253201. This is the constraint table of the question, and we can see in the table there's final value, shadow price, right-hand side value, lower boundary, and upper boundary. Lower boundary means that the right-hand side value cannot lower than this amount, and upper boundary means that the right-hand side value cannot more than this amount. Next, what is shadow price? Shadow price is the changes in the total profit when the right-hand side value increase or decrease by 1 unit. Let's see the sample. We use constraint 3 as a sample. We change the right-hand side value of constraint 3 to 1.2 million. 1.2 million minus the original value of 1.5 million, we see the changes in negative 300,000. So we multiply with the shadow price, and we know that the total profit decreases by 240,000. Therefore, the new profit after these changes is 472,000. Another example, we use constraint 4 as a sample. We change the right-hand side value of constraint 4 to 2 million. 2 million minus 1.8 million is 200,000. So, which means that the right-hand side value of constraint 4 increases by 200 million. So, the new profit is 720,000. That's all for our presentation. Thank you.